In example 2, we're going to practice constructing a confidence interval. Remember that a confidence interval, its purpose is to estimate or create a plausible region where we believe with some confidence that the unknown population value would be located. Okay, and we do that by taking a best estimate or a point estimate for that parameter. For a population proportion, the best way to estimate it is by using a sample proportion p hat. Okay, so let's take a look at example 2. A nationwide poll asked 1783 students whether they favor an hour and a half class meetings 2 days a week or just 1 hour meetings 3 days a week. 1123 were in favor of the hour and a half hour meeting. Okay. Obtaining 90% confidence interval for the proportion of students nationwide who are in favor of the hour and a half class meeting. Okay. So in this question, we're asked to construct a 90% confidence interval. Okay. So anytime we're asked to construct a confidence interval for a proportion, we must use this formula here. Okay. We need to find p hat, the critical value z alpha over 2, and then here we have a sample size and we need to calculate this value as well. Now, before we actually go into this problem, there is a prerequisite for us to use this formula, okay, and it's right here. So normality must hold in order for us to construct this confidence interval, okay? So there's two cases for normality that need to hold. The first thing is this formula here must hold true. We'll be checking that with this problem. And p hat, 1 minus p hat, must be greater than or equal to 10. And then 2, lowercase n, that's your sample size, must be less than or equal to 0.05 times capital N. Capital N is your population size. So what this means is the sample you take must be less than or equal to 5% of the overall population size. Okay. In your homework, you will always assume part 2 to be true. Okay. You will always assume the second part to be true. But the first part you will have to calculate in the homework assignment, and I'll show you how to do that with this example. So we're going to first check normality to make sure it holds, and then I'll show you how to calculate this either using the formula by hand, but I'll show you a nice little calculator function to do that as well. Okay, so first let's gather our variables. So a nationwide poll asked 1783 college students, so that's our sample size, 1783. Whether they favor hour and a half meetings 2 days a week, hour meetings 3 days a week. And notice we're going to gather a characteristic of interest here. 1123 were in favor of the hour and a half meetings. So that's going to be our characteristic of interest. Remember that p hat has a formula, x divided by n. Is that right? X is the number that have the characteristic of interest. And in this case, 1123 have that. Okay. So in order for us to check this condition here, let's plug in the formula. So in the calculator, let's check and see if we have greater than or equal to 10. So we need 1783, multiply that by p hat. So we need to take the proportion 1123 divided by 1783. Okay. And then we need to do 1 minus, and I need to do another fraction here. So that's going to be 1123 divided by 1783. Let me close my fraction. Now let me close my 1 minus. Let's check and see if that's greater than 10. Okay. So this first condition holds true. The second condition, again, in the homework assignment, you will always assume that the sample that you just took, 1783 college students, you will assume that that's less than or equal to 5% of the overall population size as far as college students go. Okay, so this condition is also met. So now that the conditions are met, now we can answer the problem. Obtain a 90% confidence interval for the proportion of students who favor the hour-and-a-half meeting. So now, let's do it here. Construct the confidence interval. Okay, now we need to construct the actual confidence interval. So the confidence interval is this formula right here. Okay, and notice we do need a few things. First, we need p hat. P hat, which is x divided by n, that was 1123 divided by 1783. Okay, now I do want to note, if you do try this in the calculator, divided by 1783, okay, it's an irrational number. Okay, you can also try to simplify if we wanted to. By the way, in the calculator, to simplify this fraction, you can hit math and then hit number 1, and what this is saying is turn my decimal into a simplified fraction. Sometimes it turns it into something very nice that we can use, sometimes it doesn't. So unfortunately, when we're plugging in p hat, we have to use 1123 divided by 1783 here, here, and here. It can be very time consuming doing this by hand, but there is a calculator function that will do this in a split second. I'll show you in a sec. Nevertheless, we do need p hat. We have one piece of the formula. We need n from the formula, 1783. We also have that piece of the formula that's going to be the bottom here. Okay, so a lot of pieces we already have. P hat, n, p hat here. The thing we're missing though is what? The critical value. So we need to find z alpha over 2. And from the previous video, the setup to find z alpha over 2 was inverse norm. The inverse norm, we needed alpha divided by 2. Well, let's go back down to the problem and see what the confidence level was. Here we're asked to obtain a 90% confidence interval. This is our confidence level, 90%. So in order to find alpha, alpha is the remaining of the 100%, right? So alpha has to take up the remaining 10% in order to complete the 100%, right? But again, we don't just need alpha, we need alpha divided by 2. So inside, we need alpha divided by 2. We can also place it inside the inverse norm function like this. If you want to call it 0.05 already, you can. And then 0, 1. So let's check and see what the critical value is going to be. So we're going to do second vars. We're going to do inverse norm. So let's do 0.10. Notice it was already there, but that's okay. Divided by 2. Okay. 0 and 1. Okay. And critical value, keep in mind from the previous video, we take the positive. Okay, so this is going to be positive 1.645. And for our case, 3 decimal places is okay for critical value. There's actually a different method of finding critical values, and that's using a manual table approach. The table is less accurate because it only goes to 3 places, but since it's an accepted way of calculating critical value, 3 decimal places is going to be fine for our problem here. Okay, so we have the critical value, we have sample size, we have p hat, right? And if we wanted to, we can go ahead and construct that confidence interval. So keep in mind what a confidence interval is. We're taking one sample and estimating the population proportion, but we need to create, because of that sample, remember sample data can always change when we move from sample to sample, So let's create a region, a plausible region with some confidence where we believe the population, the overall population value should be. It should be somewhere in there, right? And once again, in order to calculate that, we need the lower and upper bounds for this acceptable region. And that's going to be this formula here. So we need to do p hat minus z alpha over 2 square root p hat 1 minus p hat divided by n. That's going to be the lower bound. And then p hat, and then all that changes here is a plus. 1 minus p hat divided by n. This is going to be the upper bound. And we can plug in all the values that we found. 1123 divided by 1783 minus z alpha over 2. We found that to be 1.645. And then square root. And then p hat, that was the 1123. Notice this is going to be very time consuming by hand, right? I'll show you a very nice way how to do this in the calculator in a bit. And then we need 1 minus divided by 1783 divided by n. The sample size was 1783. Let's do that again. That's going to be, let's do this instead, 1783. Comma, and just keep in mind, that's barely the lower bound, right? That's barely the lower bound. We would still need the upper bound that had the plus sign, right? So that's very time consuming, very time consuming. Instead, I'd like to propose an alternate way to find the confidence interval, and it does this in a split second. That's a very nice thing. It's going to calculate all of this that we have here in a split second using a very nice calculator function. That calculator function is called 1 prop z int. 1 prop z int. Its sole purpose is to calculate this formula in a split second. It just needs a few things, a few variables, but it's able to calculate it very nicely. Okay. By hand approach is fine. Just be warned, it does take a while to do. It's very time consuming, but let me show you what this 1 prop z int looks like. So you're going to find 1 prop z int by going to stat. Notice here we typically either stay on edit or go to calc, right? So far in this semester we've been going to one or the other. This time I want you to go over one more. We haven't gone here yet in this class so far. Tests. And I want you to look for the function called 1 prop z int. Now, just a warning. If you go to number 5, it looks like the one that we want. 5, 1 prop z test is for something else. Okay, we want 1 prop z int, not test. So we need to keep looking for the 1 prop z int. Okay, notice here, A, and you hit enter. And notice it's just looking for a few things in order for it to calculate this entire formula. It needs the characteristic of interest, how many we have, sample size, and the confidence level. By default, it puts the decimal with the confidence level. Okay, so we'll do the same as well. So let's go back to the information we collected. 1123, characteristic of interest. The sample size, 1783. Our confidence level, if we go back to our problem, okay, obtain a 90% confidence interval. So let's put 0.90 into the confidence level, okay? Don't worry if the trailing zero disappears. 0.9, 0.90, we're still at 90% either way. And then hit calculate. Okay, and then hit calculate. The very first line, okay, if you notice the very first line, you have a lower number, comma, and the upper, right? Kind of like we would have here. If we actually calculated this whole thing by hand, we would get a lower number, comma, upper number. What does that mean? Remember that in our number line, okay, this piece right here, we're trying to calculate the lower bound and upper bound that creates an acceptable region, right? So it's centered at p hat, where p hat is 1123 divided by 1783, right? So the calculator right below gives you what p hat is equal to, what you entered. So p hat is 0.629. But again, can p hat change based on the sample? It can. Okay, it could have been 0.39. Okay, it could have changed if we took a different sample. So the goal is to create a plausible region that's wide enough to contain the true population proportion. And it's saying here, if you create the lower region at 0.611, and if you go all the way up to 0.648, let's call that 649, then we are 90% confident that the unknown population parameter is between 0.611 and 0.649, okay? So finishing off this problem, okay, so the 90% confidence interval will be 0.611 to 0.649.